Hello everyone. In this session I am going to explain the damped oscillation cases. So in last session we have studied the displacement equation for the damped oscillation. So that is y is equal to what we got the expression, that is y is equal to y naught by 2 1 plus b by root of b square minus omega square by root of b square minus omega e to the power of minus b plus root of b square minus omega square into t plus plus 1 minus b divided by root of b square minus omega square into e to the power of minus b minus root of b square minus omega square into t. So, this is the expression we got. So, this is the displacement equation for the damped oscillation. So, now the damped oscillation, it is depending upon the relative values of b and omega, where b is the damping coefficient and omega is the angular. So, based on that relative values, the damped oscillation is classified into the 3 cases. So, the 3 cases of damped oscillations are damped harmonic oscillator, damped harmonic oscillator can be classified into 3 cases, that is, first one is a periodic or over-damped oscillation. A periodic or over-damped oscillation. And the second one, so here in this a periodic or over-damped oscillation, the damping will be more than the angular frequency. So that is p square is greater than omega square. And next, second one is critically damped oscillation. Critically damped oscillation. So in this case the damping that is equal to the angular frequency. So and in the third case is underdamped, underdamping or oscillatory. Oscillatory. So in this case the damping is less compared to angular frequency. So like this 3 cases are classified. So now let us study the one by one, what is nothing but a periodic oscillation, over damped oscillation. So then critically damped underdamping and oscillatory oscillation. So periodic oscillation means we know the motion which repeat itself after a regular interval of time. So aperiodic means that is opposite to the periodic, that means the body will come back to the equilibrium position without oscillation. So just it will move and immediately it will come back to its halt equilibrium position. So that is aperiodic. So or else we used to call it as a over damped oscillation. So when b square is greater than omega square, then the equation, the above equation will become, so above equation the damped harmonic oscillation, that's displacement equation will become, so if b square is greater than omega square, then if we give any values that is greater than the omega square, then here the b square minus omega square is real. And it is positive. Real and it is positive. B square minus omega square is real and it is positive. So that's why the above equation will become, so at initially the displacement will be y naught. Then after that, as the time increases, as the time progresses, then at the time of infinity, so the displacement will become completely, it will become 0. So at t, when t is increasing, so when the t is increasing, then the displacement will be goes on decreasing. Okay, so when it is infinity, then this y will become, when t tends to infinity, then the displacement will be 0. So that means this is the condition under which the restoring and resistive force acting on it resistive and restoring force acting on it such that the body quickly comes to the halt at equilibrium position So condition under which the restoring and resistive force acting on it such that the body comes to the halt at equilibrium position without oscillation with the maximum time within the maximum time. So that what will happen when the displacement in the y-axis and the time is progressing, so the body from initial it is a displacement y naught, it will come back to the as the time progresses, then the displacement will become 0. So this is the case when b square is greater than omega square. So and also here it is the case of high damping, heavy damping. Here is the case of heavy damping. Heavy damping, the body will come back to its equilibrium position as quickly as possible within the time interval. It will come back to its original position. So what are the examples for this? So where we used to observe this aperiodic or overdamped oscillations in a beat galvanometer, deadbeat moving galvanometer, deadbeat moving coil galvanometer. Deadbeat moving coil galvanometer. What will happen in this the moving coil galvanometer or voltmeter? When we used to give some current, then what will happen? It will suddenly, the oscillation, suddenly it will comes to the maximum point or minimum point with the maximum time, only without oscillation. Only it will go and it will meet the maximum, and again it will come back to its mean position. So that will happen in the coil galvanometer. So that means when we used to keep the simple pendulum in a liquid that is having a more viscosity, so then what will happen? So, the body just it will move and it will come slowly, it will come back to its mean position. So, that means it will with the maximum time it will takes to come back to its equilibrium position. So, these are the example, deadbeat moving coil and simple pendulum in viscous liquid. So, that is also called as a heavy damping, it is to observe. So, the next case that is when the damping is equal to the angular frequency, that when B is equal to omega. So, the next case is second one, critically damping. Critically damping. So, in this the damping that is equal to angular frequency. So, this is the case. So, what did happen in this critically dampened? So, when we used to substitute in the displacement above equation B square is equal to omega, then therefore, we get displacement equation will become, we get, so B square is equal to omega. So, then this whole term will become 0, then 1 by 0 that will become, so 1 by this B square minus B square, suppose it will happen, then we will get 1 by 0. So, that means infinity. So, the displacement equation will become infinity. So, then it is an indeterminate value. So, we can call it as indeterminate value. So, we can't able to find out the exact solution. Okay. Then the solution will break down. The displacement equation will be break down. So, in such a cases, so we have to consider that as a, let us consider that root B square minus omega square has a small quantity, small quantity. So, let us just consider, root of B square minus omega square is equal to h, that is small quantity. To solve the displacement equation for critically dampened, so we are considering that has root B square minus omega square is equal to h as the small quantity. Okay, small quantity, h is small quantity. So, now if we consider root of B square minus omega square h, then substitute in the above equation. So, then we get y is equal to, this will equation will become y naught by 2 1 plus b divided by h e to the power of minus b plus h into t plus 1 minus b divided by h into e to the power of minus b plus minus h into t. So, we will get the equation like this. Then to simplify this further, then we have to split this equation. So, then what we will get, y is equal to y naught by 2, so e to the power of minus bt e to the power of ht plus b by h e to the power of minus bt into e to the power of ht plus e to the power of minus bt minus b by h e to the power of minus b e to the power of. So, here if we split this equation, then what we will get, e to the power of minus b t into e to the power of minus ht, then minus b by h e to the power of minus bt into e to the power of minus ht. So, we know that the exponential term when the exponential term, that is the addition of exponential term, we used to write that when we used to split that, then we used to write like this. So that only I read. Then if you observe here, then what is the common in all the terms? That you have to take it outside. So here the common term is e to the power of minus bt, that is the exponential of minus bt is common, so that we have to take outside. So then what is the equation we used to get? Let's once again, so just if we simplify, then what we got? Y is equal to y naught by 2 e to the power of minus bt. When we take the common outside, then what we will get? So y naught by 2 e to the power of minus bt, e to the power of ht plus e to the power of minus ht, and the b by h e to the power of ht plus minus e to the power of minus ht. So from the last expression. Then here this is in terms of exponential. So if we take this 2 inside, then we will get the formula, that is in terms of cos and sine. So just take this 2 inside. Then we will get the formula, that is this is in terms of cos hyperbolic and this is in terms of sine hyperbolic. So that's why this above equation become y is equal to y naught e to the power of minus bt cos of hyperbolic of ht and plus b by h sine of sine hyperbolic of ht. So this is the equation what we are getting from this. Next, write these two terms in the form of exponential. Expand this cos hyperbolic of x. So that is, we know that cos hyperbolic x is equal to, what is the formula it will give? 1 plus x square by 2 factorial plus x to the power of 4 factorial plus x to the power of 6 by 6 factorial. So similarly, sine hyperbolic x is equal to x plus x to the power of 3 by 3 factorial plus x to the power of 5 by 5 factorial. So this is the expansion of cos and sine hyperbolic. So that's why we used to get, if we put that values in this, then we used to get cos hyperbolic x. So 1 plus h square t square by 1 factorial plus h to the power of 4 by 4 t to the power of 4 by 4 factorial plus so on x plus b by h ht plus h to the power of 3 by 3 factorial, so on. Okay. So here in this, from this equation we have to, because initially only we considered that h is a very small quantity. Okay. So that's why here we have to neglect the higher order terms. So ignore the higher order terms. Ignore higher order terms because h is small quantity, because h is very small. Ignore the higher terms because h is very small. So then what we will used to get, e to the power of minus bt 1. So h square t square is higher order term. So just ignore that. Then 1 plus b by h and here h into t. So h will get cancelled. Then what we will get, y is equal to y naught e to the power of minus bt of 1 plus b into t. So, this is the displacement equation for critically damping. Y is equal to, and here this is the amplitude. So, initially it is with the y naught and e to the power of minus bt. That is, what will happen in this critically damping cases, the exponentially it is decreasing, the term exponentially decreasing, but within the short interval of time. As the time progresses, it will, as possible as early, it will come back to its mean position. So, this is in the case of b square is equal to omega square, critically damped. So, then what it says that critically damped means? It is the condition under which the restoring and resistive force acting on a body such that the body quickly come back to its halt at equilibrium position with a minimum time, within a minimum time. But in the case of over damping, what will happen? It will take maximum time to come back to its initial position. So, compared to that, in the case of critically damped, the body will immediately come back to its mean position within a short time interval. So, that what will happen in this case has quickly the body will come back to its mean position. So, without here also in this case also the body will come back to its mean position without oscillation. So, then what are the examples for this? So, we used to observe in the vehicles shock absorber, automatic shock absorber. Shock absorber. So, in car, in bike, we used to observe this critically damped oscillation. So, that suddenly it will come back to its mean position with a minimum time, within the minimum time, that is to without oscillation. Just it will move and just it will come back to the initial position without oscillation. Minimum time. So, then we can define this as, it is the condition under which restoring and resistive force acting on a body such that the body comes to halt at equilibrium position. Equilibrium position without oscillation in minimum time. So, it is the condition, what it says that it is the condition under which the restoring and resistive force will acting on a body such that the body will come back to its halt mean position, mean position at equilibrium position without oscillation in minimum time. Okay. So, this is the example for critically damped that is automatic shock absorber. In all the vehicles we used to observe the critically damping. So, that is third one, under damping or oscillator. It's called as oscillator. So, in this case the damping is very less. So when b square is less than omega square, then the above equation that will become, so when b square is less than omega square, then this equation will, this b square minus omega square is become negative, and imaginary value. So where this omega square, b square minus omega square, it will become imaginary. So that's why first we have to make into positive, in terms of positive, then only it's able to get a proper solution for underdamped. So that's why just make the some rearrangement in this equation, that is, so when in this root of b square minus omega square, because in this underdamping is very less damping, little damping we used to observe in this case underdamping oscillator. So that's why take the common of minus here, then what we will get, omega square minus b square. So here we know the value of minus 1 is equal to root of minus 1 value is I, imaginary quantity, complex number. So then this equation will become I root of omega square minus b square. So this quantity we can consider as just where omega root of omega square minus b square is equal to omega prime, has considered as omega prime, then this will become I omega prime. So root of b square minus omega square is equal to I omega prime. So then we have to substitute this I omega prime value in the above equation. So then we will get a proper solution for this. Okay. So because if we solve as it is when b square is less than omega square, then we will get the value in terms of negative. So that is will become the imaginary quantity. So that's why we are making the some rearrangement of this equation, that is making a first positive. Now substitute in the place of displacement equation I omega prime, then the above equation that will become, the displacement equation will become root of b square minus omega square is equal to what we simplified, that is I omega dash. So now substitute in this equation, we will get y is equal to y naught by 2 1 plus b by I omega dash into e to the power of minus b plus I omega dash into t, and the second term plus 1 minus b divided by I omega dash into e to the power of minus b minus I omega dash into t. So this is the equation what we got. So just split this equation, then again we will get in terms of sine and cos equation. So that is y is equal to y naught by 2 and e to the power of minus bt e to the power of I omega dash t plus b divided by I omega dash e to the power of minus bt e to the power of I omega dash t plus e to the power of minus bt e to the power of minus I omega dash t. Next the second term minus b by omega prime dash e to the power of minus bt e to the power of minus I omega prime t. So what is the equation we are getting? So here also, so what is the common, that take it outside and write in terms of so then next what we will get, y is equal to y naught e to the power of minus bt is common, and so write the common terms one side, that is here e to the power of I omega dash t plus e to the power of minus I omega dash t take this to that inside, then b by I omega dash e to the power of I omega dash t minus e to the power of minus I omega prime t. So, this is the equation we got now. The next, we have to further simplify. So, here also that will come 2. Okay. So, and this is in terms of cos x formula. So, cos we write it as this equation becomes y is equal to y naught e to the power of minus bt cos of I omega prime t. So, cos x here, so this whole term that I omega prime t, this is like x e to the power of x plus e to the power of minus x divided by 2 is cos x. So, that is in the place of x, I omega prime t is there. And next, here b by omega prime, take it as outside common, then the remaining we can take this I inside. So, then this will become in terms of sine formula, that is sine of I omega prime t. So, when the particle is oscillating with in the case of underdamping, so what will happen? So, if we consider a right angle triangle and this, the particle is oscillating with the phase constant phi and the small with the small damping, and the angular frequency is more, and here b square, so root of omega in the opposite side, so that is omega prime. So, then for this if we write the sine phi, what is the sine phi? Opposite, here the opposite side is root of omega square minus b square. So, that we can directly write it as omega prime opposite by hypotenuse, hypotenuse is omega, and cos phi adjacent by hypotenuse, that is b by omega. Then but we want b by omega prime. So, then just write it for the cot phi. So, cos phi by sin phi, then what we will get, sin phi is b by omega and cos phi is b by omega, and the sin phi is, that will become omega by omega prime. So, here omega will get cancelled, then we will get b by omega dash. So, that b by omega dash we can substitute in the place of b by omega dash cos phi by sin phi. So, then this equation will become, so that equation we will get y is equal to y naught e to the power of minus bt cos I omega prime t plus b by omega prime, we can write it that has cos phi by sin phi, sin phi into sin I omega prime t. So, this is the what we got. Here take the sin phi outside, then what we will get for further simplification, then we got cos I omega prime t. When we take the sin phi outside, then the first term will multiplied with sin phi. Cos phi sin I omega prime t. So, if you observe here this equation is in the form of sin of a plus b, that is equal to sin a cos b plus cos a sin b. So, then we will get in the place of a sin of I omega prime t plus phi. this equation. So, and then remaining terms write it, that has e to the power of minus bt by sin phi, and sin phi value we know. What is the sin phi? Omega dash by omega. So that we can substitute here. Then what we will get? Omega prime. This will come in the numerator. Why not? E to the power of minus bt omega. And again omega dash is nothing but what? Root of omega square minus b square. Okay. So this is, and this is the amplitude. What we are getting, this is the amplitude. Here also the amplitude goes on decreasing, exponentially decreasing, that is in terms of sine we got the where y naught e to the power of minus bt omega by root of omega square minus b square, that is the amplitude. We can write that has amplitude. Then this equation become a sine of I omega prime t plus phi. So this is the displacement equation for underdamped harmonic oscillator. So the particle is oscillating with the displacement y is equal to a sine of I omega prime t plus phi. This is a, where is the amplitude. When the restoring force and resistive force acting on a body such that the body will oscillate, the body will make a to and fro oscillations within a finite interval of time, then the amplitude goes on decreasing. So the amplitude goes on decreasing. So as the time increases, then the amplitude goes on decreasing slowly by making a oscillation. So like this the graph used to represent. So that means amplitude suddenly it will not come back to its mean position, it will make a oscillation with a slow motion and with the diminishing amplitude. So that's why we used to call as when the restoring force and resistive force acting on a body such that the amplitude, the body will come back to its mean position with the amplitude diminishing. The amplitude goes on keep decreasing within a short time interval. Okay. So this is the case of underdamped. The time period for this underdamping, time period formula for time period for damped harmonic oscillator, that is T is equal to 2 pi by omega prime, omega prime. But in the for SHM, what is T is equal to 2 pi by omega for SHM, simple harmonic motion. And in this case damped harmonic oscillator 2 pi by omega. So then what we will get, omega prime is root of omega square minus b square, omega square minus b square. So then if we substitute this, then omega square by m square. But omega is nothing but what? Omega square is equal to k by m and b is equal to r by 2m. So when we b is t is equal to, when we substitute these values in this above equation, then we will get k by m minus b square will become, b square is equal to r square by 4m square. So we will get r square by 4m square. This is the time period. And the frequency is f is equal to 1 by 2 pi root of m by k minus 4m square by r square. So this is the frequency for damped harmonic oscillator.